Hi everyone, today a video on carbonyl group chemistry looking at carboxylic acids and esters. So carboxylic acids have a carbonyl group within them, but it also contains a hydroxyl group, an OH group attached to the same carbon. So we write it as COOH or CO2H. And like we had in aldehydes, this group can only be found at the end of a carbon chain. Now, having these two functionalities, both the carbonyl group and the hydroxyl group on the same carbon, changes the properties of the groups. And in particular, the OH group, the hydroxyl group, is much more acidic than it is in alcohols. We don't necessarily think of alcohols as being particularly acidic, but the OH group in a carboxylic acid, sort of clue in the name, carboxylic acid, it's much more acidic. It's much more easily lost. The proton is much more easily lost. And the reason is because the acidity depends on how stable the resulting anion is. Now, in an alcohol, we get rid of our proton and we're left with a negative charge on our oxygen. But typically that's it. Our negative charge is stuck on that oxygen. In a carboxylic acid, we have the same idea, the negative charge being on the oxygen. But we also have the idea that this negative charge can be delocalized. It can be spread out across the carbonyl group. We can spread our negative charge onto the other oxygen atom as well. We can imagine an arrow from a negative charge on the one oxygen coming down to form a carbon-oxygen double bond and then breaking the other double bond that we have to make the negatively charged single carbon-oxygen bond. And because this charge is more spread out, it's a more stable anion and therefore it's more acidic. Now, carboxylic acids are named using the suffix oic acid, and the carbon atom of the functional group is counted as part of the carbon chain. So a couple of examples here on the right here. We have a 2 carbon chain length, that would be ethanoic acid. If we have a 4 carbon chain length, that's butanoic acid. Now, our standard IUPAC naming rules apply, so we always look for our longest chain. If we have any substituents, we have to number the substituents. We name everything in alphabetical order and not numerical order. So where there are substituents or side chains, we number them, and the carboxylic acid carbon is the first carbon. And again, we don't, like we had in aldehydes, we don't have to number where the carboxylic acid group is because it can only be found at the end of the chain. So an example, a couple of examples here, the one on the left, our longest carbon chain is 4 carbons long, but we also have a methyl group that is branching off the chain. The carboxylic acid carbon is number 1, so therefore the methyl group is on carbon number 3, so that's 3-methyl butanoic acid. And then likewise, if we had 2 carbon groups, 2 methyl groups on that third carbon, we use our standard IUPAC naming. We have to number every single group, so it's not just 3-dimethyl butanoic acid, but 3,3. We number every single of these methyl groups. And we use the di terminology because there are 2 of them, so 3,3-dimethyl butanoic acid. Now, when the functional group is attached to a benzene ring, like we had with aldehydes, we name it slightly differently. Essentially, we name it as a derivative of benzene instead. And so the suffix carboxylic acid is used, and the carbonyl carbon now is not counted. So if we have a benzene ring and then a carboxylic acid group coming off one of the carbons of the benzene ring, that would be known as benzene carboxylic acid or benzoic acid. Now, carboxylic acids can form hydrogen bonds with water, and so the small chain molecules are soluble in water because they can form these very strong hydrogen bonds. The acids will also form hydrogen bonding with each other, and so the reason for this is, remember that hydrogen bonding, we need to have a hydrogen attached to either an oxygen, fluorine or a nitrogen. And so in our carboxylic acids, we have our delta negative carbonyl oxygen. We have our delta positive hydrogen that is on our OH group. And if we have water, we have our delta negative oxygens and our delta positive hydrogens. And so if we're drawing out these pictures, remember that we always show all of our partial charges. So delta negatives on the oxygens, delta positive on the hydrogens. And then we show our hydrogen bond, our sort of dashed line going from the lone pair on the carbonyl group, on the oxygen of the carbonyl group, or the oxygen of the water, to a delta plus hydrogen. And so because the acids can form hydrogen bonding with each other in the solid state, the melting point is higher than the corresponding alkanes of similar MR because we have stronger intermolecular forces, hydrogen bonds versus just van der Waals forces. And the carboxylic acids have characteristic smells. So, for example, ethanoic acid is the acid that's found in vinegar, for example. Now, esters are derivatives of carboxylic acid. So you can imagine that we have taken a carboxylic acid and then we've replaced the hydrogen from the OH group by a hydrocarbon group, a carbon-based R group. Now, naming esters takes some care and quite a lot of practice. The names are derived from the acid that we started from, but the names always begin with the alkyl group that has replaced that hydrogen of the acid. And so the acid part is named from the number of carbon atoms, including the carbonyl group carbon. So like how we named the carboxylic acid, we include the carbonyl group carbon. And so generally, if we look at the names of these, and you can see I've coloured them in red and blue here to try and help you work these out. These are always named as the length of the alkyl chain that we've added. So the alkyl chain that has replaced the hydrogen is always first, and then the length of our sort of carbonyl bit of it is afterwards. So the first example here is propyl methanoate. This is because we have the alkyl chain that's replaced our hydrogen that was in the carboxylic acid is 3 carbons long, so propyl. And then we have our sort of the acid part of that chain, the carbonyl group bit of it, which is 1 carbon long. So this is named as propyl methanoate. And so when we name esters, it's always ending in the O8. So we have the length of the carbon chain attached to the oxygen is always named as kind of propyl, ethyl, ending in ly. The name of the carbonyl part of it always ends in O8. So it's propyl methanoate. The second example, we have 2 carbons attached to our oxygen. So our alkyl length chain is 2, so that's ethyl. And then our carbonyl part of this, you can see there are 3 carbons. We have CH3, CH2, C double bond O. So this is ethyl propanoate. The example on the bottom left, we now have only 1 carbon group, 1 carbon length chain attached to our oxygen. So the alkyl part of it is methyl. And then we have a 4 carbon chain for our carbonyl section, so methyl butanoate. And then finally, the bottom right example, we have a 3 carbon chain attached to our oxygen, so that's propyl. And then we have a 2 carbon chain for our carbonyl part, so propyl ethanoate. And so generally when we name them, we name it as the O alkyl length, propyl, ethyl, for example, and then the carbonyl length, and ending in O8, so propyl methanoate, ethyl propanoate, for example. Now the short chain esters, because they're much shorter chains, they have much lower MR values, they're fairly volatile and they have fairly pleasant fruity smells. So they're often used in flavouring in perfumes. They can also be used as solvents and plasticizers. And we might hear the terms fats and oils, and these are esters with much longer chain carbon groups. So if we look at the reactivity of carboxylic acids, the carboxylic acid group is really heavily polarized. We've talked in the previous video about aldehydes and ketones and how they have a very polar CO bond, and so our carbon is electron deficient, delta positive, because oxygen is so much more electronegative. We have that dipole, and so we have delta negative on the oxygen. Well, carboxylic acid groups are even more heavily polarized because now we have 2 carbon-oxygen bonds. So we have 2 oxygens, both electronegative, pulling electron density away. And so that means that our carbon is even more electron deficient. And it leads to multiple reactivities. Like we saw with aldehydes and ketones, delta positive carbon can be attacked by nucleophiles. The delta positive part of that is very electrophilic, electron deficient. We have our so nucleophiles, electron pair donors can attack that. The delta negative oxygen, the carbonyl oxygen, can be attacked by electrophiles. So this, for example, is where potentially we could protonate it, adding a proton to it, because that carbonyl oxygen is delta negative. It still has lone pairs, so that can act to essentially almost acting as a base in that case, reacting with an acid. Or the delta positive hydrogen that is on the OH group can be lost as an H+. In this case, it behaves as an acid. And we talked a couple of slides ago about why that it's much more acidic than an alcohol, because of the stability of the resulting anion, the carboxylate anion. And so just here I've explained this again, that when we lose the proton from the OH group, we have our carboxylate anion remaining. And the negative charge can be not only localized on the 1 carbon, but shared between the 2 carbons. It's shared over the whole of that group. And the resulting delocalization And this is similar to the kind of delocalization we see of the p orbitals in alkenes to make the pi bond. It's similar to the delocalization that we see in benzene to make our pi system. This delocalization makes the resulting ion more stable. Anytime where we're spreading this electron density over multiple atoms makes things more stable. And the more stable the anion is, the more acidic the species is. So carboxylic acids are weak acids, and so the equilibrium lies well towards the left, well towards the reactants. They hardly dissociate into H plus and the anions. However, they are still strong enough acids to react with things like sodium hydrogen carbonate to release CO2. So this is our general reaction of an acid plus carbonate to give us salt, water, and CO2. The release of CO2 is quite often called effervescence, and this is actually the basis of another distinguishing test. Alcohols don't do this, so we can tell the difference between having a carboxylic acid OH and an alcohol OH group in essentially how acidic they are. And so this could be very useful if, for example, to be able to tell the difference between two solutions that we know either contains a carboxylic acid or an alcohol, but we're not sure which is which. And so we can write our equation down. For example, here we have ethanoic acid reacting with sodium hydrogen carbonate. This produces sodium ethanoate, the ionic salt, and then water and CO2. Now, carboxylic acids, as we said, are acids. They're proton donors. They show the typical reactions of acids. They form ionic salts with more reactive metals, alkalis, metal oxides, or metal carbonates, as usual. And the salts that are formed are called carboxylates, and they're named after the parent acid. So, an example, ethanoic acid plus sodium hydroxide makes this salt, CH3COONA. And so we name it from the parent acid, so it was ethanoic acid, and so the salt ends in ethanoate. Because it's a sodium salt, sodium ethanoate. Notice how it sort of seems a little bit similar to the naming of the esters. For example, we might have something like propyl ethanoate as an ester. Here we have sodium ethanoate as our salt. Another example would be ethanoic acid reacting with sodium carbonate, or sodium bicarbonate, and this produces sodium ethanoate, the same salt again, water and carbon dioxide. So remember, it's acid plus base gives us salt plus water. Acid plus carbonate gives us salt, water, and carbon dioxide. So then comparing it to the reactions of esters, well, carboxylic acids will react with alcohols to form esters. And this is accelerated by a strong acid catalyst. It's a reversible reaction, and it forms an equilibrium mixture of reactants and products. So generally we take a carboxylic acid, we take an alcohol, we take some sort of acid catalyst, and overall it ends up producing an ester, and this is a type of condensation reaction. We're kicking out a small molecule, in this case water. And so you can see you have the OH group of the carboxylic acid, the H group of the alcohol, joining together to make H2O, and then the two other bits join together. So our RCO double bond and our OR, the alcohol, join together to make our ester. And we'll look at the mechanism of this on the next slide. But the carbon of an ester is still delta positive, and so it can be attacked by water acting as a nucleophile. And so this is the reverse of the reaction above, and this is called the hydrolysis reaction. So imagine reaction at the top here, not going from left to right, but going from right to left. Water reacting with our ester, essentially splitting apart the ester back into the original carboxylic acid and the alcohol. Now, because this is an equilibrium reaction, we're not going to completion. And so we have an equilibrium mixture, a mixture of the ester and the carboxylic acid and the alcohol. And the acid is just a catalyst, and so it only affects the rate of the equilibrium attainment. It doesn't affect the equilibrium composition. Remember that catalysts do not affect whether it favours going forwards or backwards, but it affects the forwards and backwards rates equally, so it doesn't affect the position of equilibrium, just affects how quickly we can get to equilibrium. So we can use our acid catalyst to accelerate the rate of ester hydrolysis at room temperature. A base catalyst can also be used, but if we use a base catalyst, say for example sodium hydroxide, we end up forming the salt. So sodium ethanoate is shown at the bottom right. If we started with ethyl ethanoate plus sodium hydroxide, we would make sodium ethanoate and ethanol. Now the base catalyst removes the acid from the reaction mixture, and the reason, sort of the way to think about this is that we take a aqueous solution of sodium hydroxide, so essentially we have some water in there as well. We have our hydrolysis reaction that we see normally of an ester plus water. this would produce a carboxylic acid and an alcohol, but because we're doing it in a base solution, we have our carboxylic acid, which is an acid, we have our sodium hydroxide, which is a base, and so we have an acid-base reaction, like we saw on the previous slide, to form the salt. This is a sodium ethanoate. And so in this case, the reaction does go to completion. It does go all the way, because once we form that salt, the sodium ethanoate, we can't get back to it in this base solution. We can't go backwards. It's a complete reaction. So just looking at the mechanism, and I'll check with your example whether you actually need to know the mechanism for this. But the mechanism here to create an ester from a carboxylic acid and an alcohol, it's an example of a nucleophilic addition-elimination mechanism. And so we start off with our carboxylic acid. The reason why we do this under acid catalysts is that our carboxylic acid is already quite electrophilic. We've got that very delta positive carbon. But by putting some acid in there, what actually happens is the lone pair on the carbonyl oxygen can act to pick up that proton, essentially act as a base and pick up that proton. That was one of the reactivities we talked about a few slides ago. So we can protonate that carbonyl oxygen. It's quite basic. And what this does, by using the lone pair to form a bond to the H plus cation, that's a dative bond, both electrons from our oxygen being used to make that bond. We end up now forming an oxygen with 3 bonds, and so we have a fully positive oxygen. And what this does is actually make the carboxylic acid molecule even more electrophilic. And so this increases the rate of reaction. So once we've created this very electrophilic species, we then have our alcohol, which comes in. This acts as a nucleophile because we have lone pairs on our oxygen. So we have an arrow from our nucleophilic part, the lone pair on the oxygen, the electron density. Remember that arrows always go from high electron density to low electron density. So our arrow goes from the lone pair to the delta positive carbon. Again, carbon can only have 4 bonds. We have to break one. The weakest bond is the pi component of that carbon-oxygen double bond. And so we have an arrow from the centre of the carbon-oxygen double bond ending up on the electronegative oxygen. Now remember that every step has to balance in terms of charge, in terms of atoms. So in every step of this, we've overall had a positive charge. Now our positive charge is on the oxygen that came from the alcohol. This is because we've made a bond using the oxygen lone pair. So the oxygen now has 3 bonds. So we have a positively charged oxygen. And now we have something called a proton transfer. And all we mean by this is that the H that's attached to our alcohol, where we have our positive charge, essentially just moves over to the other oxygen. And this is the oxygen that was already present as part of the carboxylic acid. And I've shown it here as the red OH group. And so our proton simply just moves from the one oxygen to the other oxygen. We call it a proton transfer step. And so in doing so, our alcohol part of this now becomes neutral again. We just have OR, an oxygen with 2 bonds. And our OH in red has now become an OH2. Again, our oxygen now has 3 bonds, and so our positive charge is on that oxygen. So we've had our nucleophilic addition part of this mechanism. We now have our elimination part. And so the way we do this is we reform our carbon-oxygen double bond. So we have our lone pair from the oxygen that was originally the carbonyl oxygen, reforming our carbon-oxygen double bond. So an arrow from the lone pair into the centre of the carbon-oxygen bond. And again, carbon can only have 4 bonds, so we have to break one of the bonds, and the bond that breaks is the carbon-water bond, essentially, whatever the bond is to the positively charged species. And so we have an arrow going from our centre of our carbon-oxygen bond to the electronegative oxygen. And so this kicks off a molecule of water, and that's how we lose our water. And then remember that our acid that we started with is a catalyst, so we need to reform it. And so in doing this, that arrow where we've reformed our carbon-oxygen double bond, we still have a hydrogen attached to that oxygen. And so again, we have a 3-bonded oxygen, 3 species bonded to that oxygen. So it's positively charged, and so we just simply lose an H plus cation. And so the arrow for that, think about the electron pair moving from the OH bond onto the oxygen and leaving the hydrogen without any electrons. So an arrow from the centre of the OH bond ending up on the electronegative oxygen that's happy to accept those electrons because it's electronegative. And so in doing that, we've lost water, we've reformed our acid catalyst, and we've created our ester. So the uses of esters, we talked earlier about oils and fats. So animal and vegetable oils and fats are the esters of the alcohol propane 1,2,3 triol. and the kind of non-systematic name is glycerol. And I've shown this over here on the right. Now, oils and fats contain 3 molecules of the long-chain carboxylic acids called fatty acids. And since they're based on glycerol, they're often referred to as triglycerides. So essentially, we've taken the reaction we've just seen, a carboxylic acid and an alcohol coming together to make an ester. But when we have it with triglycerol and essentially three carboxylic acids, 3 of these fatty acids, this creates a triglyceride. Now, the same kind of reactivity we saw, we can do that reaction to form the ester, and we can hydrolyze our esters to get back to the carboxylic acid and the alcohol. So fats and oils can be hydrolyzed in acid conditions to give back the mixture of glycerol and the component fatty acids. We can also hydrolyze them by boiling with sodium hydroxide. Now, both products of boiling it with sodium hydroxide are actually useful, and it's also a better reactivity because we have a complete reaction rather than an equilibrium reaction. And the reason why both products are useful, our glycerol and our mixture of sodium salts, is that the sodium salts are essentially soap. Now, the type of soap depends on the fatty acid that we have initially, but the sodium salts are ionic at the end. In forming it, we have our carbon double oxygen bond, our carbonyl group, and then we have our single bonded carbon oxygen. And in a carboxylic acid, that would be OH. In the salt, we've got ONa. And so I've shown this down here at the bottom. And so these sodium salts are ionic and they dissociate, and so we have this what we call an RCOO-, essentially this carboxylate end of it. And so essentially this carboxylate end of it is polar, and we call it hydrophilic. It likes water. Being a polar part of the molecule, it likes the polar water molecules, and so that part of it is soluble in water. The other end of it would be a very long chain non-polar carbon group. And so while the short polar end is hydrophilic, this long non-polar end is what we call hydrophobic. It doesn't like the polar water molecules, it likes non-polar things such as oil. And so it will be able to mix with grease, for example. So the hydrocarbon part of it mixes with the grease, while the carboxylate ionic end of it mixes with water. And so these molecules allow water and grease to mix, and therefore it allows cleaning to occur and to remove the grease. Now, going back to glycerol, we've got 3 OH bonds, and so it readily forms hydrogen bonds, and therefore it's very, very soluble in water. And the glycerol, we said, was also a useful product, and it has many uses. It's used in pharmaceutical and cosmetic preparations. As it attracts water, it prevents creams from drying out. It always has some sort of water along with it, so creams don't dry out. It's also as a solvent in medicines and toothpastes, a solvent in the food industry for food colourings, and it's also used to plasticize many materials. Now, if you've seen the video on addition polymerization, we'll have talked about plasticizers. Plasticizers are molecules that introduce themselves between polymer chains, and essentially they reduce the intermolecular forces between the chains of the polymer, and so therefore the polymer molecules can now move over each other, slide over each other, be kind of stretched more easily, and so the material becomes much more flexible and smooth. So the key thing is that we take glycerol and 3 fatty acids, we can make a triglyceride. If we do the hydrolyzation of that in sodium hydroxide, we end up forming the glycerol, which has many uses, and the sodium salts, and these are essentially soap with our polar carboxylate end that mixes with water, hydrophilic, and our non-polar hydrocarbon chain, which is hydrophobic and mixes with oil and grease. So, time to have a go at some questions. If you want to have a go, pause the video and the answers will be on the next slide, but we've got some naming of some carboxylic acids and esters, and then to draw the mechanism for the reaction of ethanol with propanoic acid under acid catalysis. So the first one was to name the molecules. So we're going to use our standard IUPAC naming rules for this. We look for our longest chain first. We look to see what our functional group is. Is it a carboxylic acid at the end of a chain, which will have a C double bond O and an OH group? Or is it an ester, which will be somewhere in the middle of the chain with a CO double bond and an oxygen connected to some alcohol group? And then we also look for our substituents. Do we have any of them? And if we do, we have to number them and then name them in alphabetical order, not numerical order. So the first example is a carboxylic acid. We have a COOH group at the end of the molecule. And if we look to see what our longest carbon chain is, it's 6 carbons long. Remember that our carboxylic acid is carbon number 1, so we have a 6 carbon length chain, so we're going to be ending our molecule with hexanoic acid. And then we just have to look for our substituents, so we can see that we have 2 methyl groups on carbon number 2, we have a bromo group on carbon number 3, a hydroxy group on carbon number 4, and an amino group on carbon number 5. And remember that while the OH is normally an alcohol and the suffix ol, because the carboxylic acid takes priority, we have to use the prefix hydroxy. And likewise for the NH2 group, normally if that was on its own it would be an amine, and we use the suffix amine. But because we have the carboxylic acid, that takes priority, and so we have to use the prefix amino. And remember that we name them in alphabetical, not numerical order. So this is 5-amino, 3-bromo, 4-hydroxy, 2,2-dimethyl hexanoic acid. And remember, if we have multiple, we have to name it using the di, tri, tetra terminology, and also number every single one. So 2,2-dimethyl, not just 2-dimethyl. Second example is a ester. Now remember, when we name our esters, we always name it first of all with the alkyl chain that has replaced the hydrogen if it were a carboxylic acid. First, so we look at our alkyl chain connected to the oxygen. That's 2 carbons long, so an ethyl chain. Then we have our sort of carbonyl part of it. Now if we look for the longest chain here, we have 4 carbons, so it's going to be based off a butane chain. So with being an ester, remember we name it with the O8 ending, so this is going to end in butanoate. And then the only thing we have to be careful of here is that we also have a bromo substituent, and this just gets added before the end of the chain name in parts. So we end up with ethyl 3-bromo butanoate. The second one of these esters, essentially the third molecule we have to name. Again, we look for our carbon chain that's been attached to our oxygen, essentially what's replaced the hydrogen. And so in doing this, we now have a 3-length carbon chain, so it's based off a propyl, but we also have some branching on that chain with a methyl group sticking out. And so we have to, again, because we've got a substituent, like we would normally name if we had a normal alkane, we have to number that substituent and name it. So this is 2-methyl propyl. And then we have to look for our carbonyl part of it, which is 2 carbons long, and so it's going to be named ethanoate. So the name becomes 2-methyl propyl ethanoate. Now notice the slight difference here in that when we have our, if it's our carbonyl part of it that has some substituents, we name that before the sort of ester part of the name, before the butanoate or the ethanoate. But if we have our substituent part on the alkyl chain that comes off our oxygen, then we name that before we name the alkyl bit. So it's ethyl 3-bromo butanoate and 2-methyl propyl ethanoate. And the second question was to draw the mechanism for the reaction of ethanol with propanoic acid under acid catalysis. So this is exactly the same mechanism that we saw a few slides ago. Under acid catalysis, we have our carbonyl oxygen. We said in the reactivity slide that our carbonyl oxygen can act as a base. It has lone pairs. It can pick up a proton. So under acid catalysis, we have acid there. It's going to pick up an H+, a proton. So an arrow from our lone pair on the oxygen to our H+. Remember that this is a reversible reaction. It's an equilibrium reaction, so we have to use our equilibria arrows, not our normal full reaction arrows. Then we have our ethanol, our alcohol, our nucleophilic part. It's going to attack the electrophilic delta positive carbon. Remember that by sort of protonating our carbonyl oxygen, we've again made this molecule even more electrophilic, even more electron deficient. So we have an arrow from the lone pair of the alcohol oxygen to the delta positive carbon. Carbon can only have 4 bonds, so we have to break one of those bonds. We break the pi bond, the weakest bond, and so an arrow from the centre of the CO bond to the electronegative oxygen. We then end up forming this tetrahedral intermediate, and this is where we get our proton transfer step. So we have our, remember that every step has to balance in terms of charge. Overall, we've always had a positive charge. So our positive charge in this, the third molecule here, is on the oxygen that was from the alcohol, because we've now got 3 bonds to that oxygen. But what we're going to do simply is move the proton, move the H+, from that oxygen onto one of the OH groups elsewhere on the molecule. So we have our proton transfer step, our alcohol bit just becomes the O alcohol chain section, now a neutral bit, and the positive charge on another oxygen, the one that we've put the hydrogen on, because that now has 3 bonds. So that's our nucleophilic addition part of it. We now have our elimination, because remember it's a nucleophilic addition elimination mechanism. So we draw our arrow from one of our oxygen lone pairs to reform the CO double bond, to reform the carbonyl group, so down into the middle of the CO bond. And then carbon can only have 4 bonds, so we have to break the carbon-oxygen bond, that is the water that has the positively charged oxygen attached. So an arrow from the centre of that carbon-oxygen bond to the electronegative oxygen. It's happy to accept those electrons. And so in doing that, we lose the molecule of water. This then produces nearly the final product, but remember that we had acid catalysis, i.e. we have to reform the acid. In reforming the carbonyl group, we still have our hydrogen atom attached, so it becomes a positively charged oxygen with 3 bonds. And so we simply lose the H plus catalyst, an arrow from the centre of that OH bond onto the electronegative oxygen. We regenerate our acid catalyst, and we form our ester. And if we're asked to name this, remember that we name it using the alcohol chain part of it first, which is in this case 2 carbons long, and then we have our carbonyl length chain, which is 3 carbons long, so it's ethyl propanoate. So thank you for watching this video. You can find lots more videos like this on my YouTube channel. If you found this video helpful, please leave a review on the tuition website. And I offer online tuition for chemistry, so please check those websites if you're interested in that. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.